Okay, so for today we're doing thermal stress. So fun. Thermal stress is going to be very similar to normal stress. Hopefully you remember the formula. The normal stress formula is how stress is equal to force divided by the cross-sectional area, which is awesome. We're going to tie a bunch of formulas together again, so let's review them. We need to know what thermal stress is. This is what thermal stress is. But where does thermal stress come from? Thermal stress comes from two things. One is the strain. Remember how strain is delta L over L. As something changes in length divided by its original length. Then finally, we have elasticity. Elasticity is stress over strain. And we have one more formula, which is the thermal expansion, which is where the thermal part of this comes in. So thermal expansion is delta L is equal to alpha L delta T. Wonderful. Alpha is your coefficient of thermal expansion, original length, and the change in temperature. Very nice. So what we're going to do now is we're going to combine these formulas all together to simplify it, to make our lives a little bit easier. So we're going to start with our thermal expansion formula because we're talking about changes in temperature today. So delta L is equal to alpha L delta T. What we're going to do now is we're going to kick this guy over to the other side of the equal sign. So delta L over L is equal to alpha delta T. Now we know what delta L over L is because it's right there. So this is equal to strain. Thermal strain is this. It's just alpha times your change in temperature. Yes, it is. Now, what we can do now is take this and combine it with elasticity. We're going to change the formula just a little bit to get rid of the fraction. How stress is going to equal elasticity times strain. It's the same thing. But now what we're going to do is we are going to combine it with this guy here. So we know that stress is going to equal elasticity times strain, but strain we already have an expression for right there. So this is going to be alpha delta L. All right, and this is what we're going to use for thermal stress. Now, if you can't remember that, you could always just reinvent it like I did real quick. It's really not that bad, but this way it cuts out a bunch of your numbers, so we don't need to worry about it. Let's do a practice problem. So for our first one, we have in a constrained tube, we have a tube here. It's gorgeous. A steel tube is 10 inches in length, placed between two large, rigidly fixed ceramic blocks separated by that far. Okay, shown in a region below, the cross-sectional area of the tube is 1 inch, and it's heated from 80 to 480. Now, we're going to be dealing with English units here, which is annoying, but fortunately, our constants are in pounds per square inch and Fahrenheit, so we don't need to worry too much about it. All right, so what we're looking for here is we are going to be looking for the thermal stress. Oh, and we're going to make this just a little bit easier because we're trying to keep it simple here. We're going to say it fits right in there. It's perfectly fit in. We'll worry about the that other part of it tomorrow. So we're just going to fit it right in. And what's going to happen? Well, your thermal stress is going to equal your elasticity times your alpha times your change in temperature, right? Because as it gets warmer, it will expand. As it expands, there will be strain. As there is strain, there will be stress. And we're fitting all of that in together. So we know what all of these numbers are. Our modulus of elasticity is 30 mega-psi. So we're going to have 30, and mega means million. So 30 million, or as the cool kids like to do it, 30 times 10 to the 6. Now, we're going to multiply that by our alpha, which is there, which is 7 times 10 to the minus 6. You betcha those cancel out. Times delta T, we're going 80 to 480, so our change in temperature is going to be 400. We multiply those all together. and we are going to get 84,000. And this is going to be in PSI because we're using yucky imperial units. You could also write 84 kilo PSI. Kilopound square inch, probably. Whatever. Okay, so that is the stress in the tube. Let's do one more. So we've got a rod of this kind of steel, whatever that is, 0.5 meters long, heated from 20 to 80, while its ends are rigid. Determine the type and magnitude of the stress that develops. All right, type. Let's talk about type. Type is easy. What's going to be happening as you heat this pipe up? The stress is going to be compressive stress because it wants to expand, but the walls are pressing on it and not letting it. So this is going to be compressive stress. All right, moving on. Now we need to determine the magnitude. So magnitude is easy. So at 20 degrees, this rod's stress-free. Do you remember those days? Anyways, so we're going to have stress is equal to modulus of elasticity times alpha times delta t. Your modulus of elasticity, I wrote it up here for you, is 200 gigapascals. 200 giga, remember, is billion, one above million. So it's going to be times 10 to the 9 times alpha. Alpha is down here, steel is 17. 17 times 10 to the minus 6, so these won't cancel out exactly, times delta t, we're going 20 to 80, so we'll just have a 60. And then multiply, multiply, multiply all of these together, and we get a big number. Let's switch it to our prefixes here. So 204 gigapascals. That's how much stress is going to be on the rod. Awesome. We'll give you some practice with these. Have fun.